Hi everyone. In the last video, we were able to discuss gradient descent algorithm and we were able to derive few important properties related to learning rate and convergence. However, there are many other optimization algorithms apart from the gradient descent algorithm which we have. We will be discussing few of them in detail over here, and a lot of them are similar to the way gradient descent algorithm works. The first algorithm which we will be discussing is resilient propagation algorithm or RProp algorithm. We will discuss its working with the help of a small numerical example first. So let's consider the same loss function as we did previously. This was the loss function we had, and this is the gradient of the loss function, and we were able to write it in this form because we assumed G as grad of LW in the previous video. Now let's consider a scenario that let's assume we have propagated till time t minus 1 and we get the value of wt minus 1 as 1 and wt as 2. By the way, for this example, we know that the optimal value is 1.5 only. We have to run any algorithm, optimization algorithm to be more precise in such a way that we reach somewhere to 1.5 and the loss is. Now let's consider the case one we have over here. We calculate the gt minus 1 because wt minus 1 was 1. On doing so, we get the value as 8 into 1, the wt minus 1 value minus 12, which is minus 4. The gt minus 1 is minus 4. Likewise, at time t, we had the value of wt as 2. On substituting wt as 2, we get the value of gt as 4. So we have two values of gradients as of now, gt and gt minus 1. We multiply both of them and we get the value as minus 16, which is less than 0. Now we pick up a value beta. This is again a hyperparameter which will be given to us. So we will be selecting initially. Since this term is less than 0, we multiply the deviation with beta and add it to the previous weights. Like we were at time t minus 1, then t happened. We need to find the value at time t plus 1. This we need to find out. We know these two terms. But now at time t, we are getting a gradient such that if we are multiplying with the gradient at time t minus 1, this is negative, and then this is the updation rule we are considering, and why we are considering it I will come to it a bit later, but as of now just consider that when the product of two gradients is less than 0, this is the updation rule we consider. So del of, or this is like the successive difference of wt is equal to wt minus wt minus 1. We write it over here. Now we put it wt, the value of wt was equal to 2 and the value of wt minus 1 was 1. We substitute and we get the value of wt plus 1 as 1.1. Now we consider another case. So this was case 1 and this is the gradient updation rule we used for case 1. This is the gradient updation rule. We will come to what it exactly means in a bit, but just consider the case that we got two gradients at time t minus 1 and time t, the product of which was negative. Now we consider the case 2 where wt minus 1 was half and wt was 3 by 4. The gradient at time t minus 1 was minus 8 and the gradient at time t was minus 6, and subsequently we get the product of gradients greater than 0, just opposite to what happened in the last class or in the last case. Here the gradient updation rule will be like this. We are at time t plus 1, we will just take the value at time t and use the same eta into gradient wt. Eta here is a term which is different as compared to what we did previously. Like in the previous case, we had the value as beta, which was 0.1. Here we will have eta, which is greater than 1, which is 1.5. Now on solving it, we get the value of Wt plus 1 as 1.5. Now here is how the updation rule looks like. So we have Wt and Wt minus 1. We can calculate Gt and Gt minus 1. Now if the product of both the terms is greater than 0, this will mean that we are propagating along the same path. That is, if Gt is negative and Gt minus 1 is negative, we are propagating in the same path. Likewise, if Gt is positive and Gt minus 1 both were positive, we are propagating along the positive path. Since we are propagating in the same path, we will take a step with more confidence, and hence we will add a term eta which is greater than 1, and we will add it to the successive differences of Wt. And this del of Wt, as we were able to find out previously, this was Wt minus 1. Now on proceeding further, this is the updation rule if both the gradients are greater than 0. Now we may get a scenario when one of the gradients is less than 0, which will mean that we were initially going in a path and now the path has changed. So ideally Gt may be greater than 0 or Gt minus 1 is less than 0. When both the things happen, the product is less than 0, which will mean that the new weights, which is the Wt, resulted in the change of path, which is not actually giving me a good value. Then we need to penalize it. So for doing that, we say that revert back to the path where we were traversing initially, which is Wt minus 1. We are not going to go to the path of Wt because it took me into a different direction altogether. We will not go there, but we will come back at Wt minus 1 and take a very small value or take a very small step in the direction of the deviation which we have captured. So this is how it will work. The updation rule will work when at least one of the two gradients is negative. So this is the entire RProp updation rule. In our scenario, we considered the case 1 where both the gradients were negative. So we had the value of Wt minus 1 as 1, Wt as 2. We know that the optimal value is 1.5. We knew it. And now if we are selecting Wt as 2, we have already crossed the optimal value. We want, now if I have to apply a gradient descent in this scenario, that we were at initially 1, now we are at 2, then there is a good chance that we may not even hit the optimal value of 1.5. We may be diverging forever. But what we know is we have the option to take a step back, come to 1, and then slowly and progress in the right direction because we know where the wrong direction is at this point of time. On doing so, we follow the updation rule and we say that at time t plus 1 we have to move to 1.1. Now we listened only to the updation at time t minus 1 where we knew that okay, we are propagating in the correct direction. We didn't listen to t, and at time t plus 1 we are at 1.1. Now we will take a step ahead and move to time t plus 2 and then keep propagating till the time we get the optimal value close to 1.5. Now this was the first case when the gradients were having different signs. Now let's consider the second case which we discussed. Here both the gradients were having same sign. Initially we were at half, which is 0.5, and then we moved to 0.75. The sign of gradient remained same. Now we were sure that we are moving in the right direction. We put more confidence to the deviation which we have between 0.75 and 0.5 and proceed further. On doing so, we get the updation rule when the product of gradients is greater than 0. We select the value of eta to be 1.5 because we are pretty much sure that we are moving in the right direction. We put more confidence to the difference between the successive weights and eventually we get the value as 1.5. Over here, even though we took a risk of selecting the value of eta as 1.5, we were able to get the result as 1.5 in just a step. So we were at Just see the progression over here. We were at 0.5. In the next step, we reached 0.75. We knew that we are in the right direction. In the next step, we are at 1.5. So the convergence is happening much faster over here as compared to the gradient descent updation rule. So this is one of the many other optimization algorithms which we are going to discuss. Resilient prop is one of them. This is the updation rule we have for the resilient prop algorithm. We should be having the weights at the lag of 2 time at any t plus 1, which means that if we are at t plus 1, we should be knowing the weights at time t and the weights at time t minus 1. Also, we need to know the eta and beta as well. Eta is a term greater than 1 and beta is a term less than 1. We can propagate using these rules related to the gradients, and in finite number of steps we can get the results. Here we will discuss another variant of gradient descent but with a momentum update. So this is how it goes. The traditional gradient descent, if I have to write it, it works like this: Wt minus eta times Gt, and this Gt is gradient of the loss function at Wt. Now, now we will add one more term to this update, which will be like Wt plus 1 is equal to the gradient descent update of Wt plus 1. Let me write it in the form of G plus beta times delta of Wt. And this delta of Wt is Wt minus 1. So this is nothing but just the gradient descent with an additional advantage that we take a track of how far we are going along each direction. So we are trying to give weights to the successive difference of. So here we are assigning weightage of beta to successive difference in the weights we have determined till now. And just be a bit careful that this is the gradient and this is the successive difference. So this delta, this is the inverted triangle delta for gradient. This triangle is for successive difference. And to make things a little bit clear, this is the momentum update rule. We take the Wt, we have the eta times Gt. This exactly is the terms which I'm highlighting over here. Will form the gradient descent update rule, and we just impute the term beta times delta of Wt. Right. Now, if I have to expand it, this is how it will look like. So I replace t with 0. This will be W1, which will be equal to W0 times beta delta W0 minus eta G0. Now delta W0 is 0. This term will be vanishing because we are starting with 0. We can't find successive difference in any case. So the first term is exactly similar to the gradient descent term, and then we move further to the second term. We do find W2 by substituting t is equal to 1 over here. On doing so, we get W1 beta times delta W1 minus eta times G1. So since we know W1, we can find out G1 easily from the last step. Now this delta times W1 is W1 minus W0. We were able to find W2 over here. So we have found out W2 over here. Now with W2, we can find G2. Now this will help us to form W3, which we can do by considering the momentum update rule and putting T as 2 over here. We have W2, we have beta delta W2, eta times G2, and this delta W2 is W2 minus W1 as mentioned in this formula, and G2 we have determined a step before as soon as we were able to form or able to find W2, and we will proceed iteratively, and this is how we are going to apply in the example which we selected. We have LW, this is the loss function. Now we were able to find L dash W, and this is GT or the gradient of T, a gradient at Wt. We start with W0, eta as 0.2 and beta as 0.1. Both eta and beta are hyperparameters which we need to select before proceeding. So the W1, as we discussed previously, is going to be W naught minus eta G naught. We do that. We, since we know W0, we can calculate G0. We do it and we get minus 0.6 as a result. We proceed further to calculate W2, and W2, as we calculated before, it is beta times, this is the value of W2 which we have. We just make successive substitutions, like we know W1, we know G1, we know W0, and on substituting everything, we get the value as 2.2. Now we proceed with W3 and then we solve further. Eventually, we are getting at fourth step the value of LW as 1.5. So here we are able to get convergence with the exact same initializer in just 4 steps. So this was the update rule which we needed. Just we considered the gradient descent update rule, as we have defined previously, and then added this extra term to it. On doing so, we were able to get the convergence in a much faster way. So this was the gradient descent with momentum. Now we proceed further with another optimization algorithm. So this is another gradient descent algorithm, or a variant of gradient descent algorithm, whose weight updation looks like this. So we have Wt and beta times delta Wt, or both these terms are exactly the same as the momentum gradient descent algorithm which we discussed a bit above. The only difference is, instead of using gradient of L over here, we take the gradient of L with respect to the updated terms, which is Wt plus beta times delta Wt. So exactly the term which we were able to find out previously, means Wt plus beta times delta Wt, which was over here. We have to put it in the loss function and then take the gradient with respect to Wt. The eta will actually be the learning rate, which we have already defined previously, and this is how it is going to work like. So we have LW. This is a numerical example, the same numerical example I have picked up. This is the gradient of LW, which we find over here. So the gradient of L, now in place of W, I substitute it with Wt plus beta times delta Wt. We get this as an outcome because W is replaced with this term. Now we take the leverage to use the fact that delta times Wt is equal to Wt minus 1 over here in this term, and we solve it further to get the loss term as this. Now since we have got the updation rule, so we have got the big calculation done in the updation rule over here, we proceed further with the same set of assumptions as we did previously to calculate um, the successive weights. So we start with W naught. We start with T is equal to 0. Over here we put T is equal to 0. I'm talking about this equation. So we will be able to get W1 is equal to W0 because T is 0 plus delta W0 minus eta times this term. Now if we look carefully, delta W0 doesn't exist. So we will be just doing the first step of gradient descent algorithm only. Now we move further and try to calculate W2, and if I have to calculate W1, I will just substitute W naught as 5, which we just assumed over here, eta as 0.2, which we have assumed, and gradient of L with respect to W naught is 8 into 5 minus 12. This is the first result we are getting. Now I have to calculate W2. We put T as 1, and this is the result we need to find out. Now this term we have already found out a step before, the gradient of L of Wt. This is exactly what I was talking about. I make a substitution over here with respect to 1, and on doing so I am getting a result which looks like this. Over here, I know both the terms W1 and W0. We just need to substitute it. And on doing so, we get the value of W2 as minus 1.704. So just the substitutions we are using, we know W1, we know W1 over here, W0 we know, beta we assume. This entire term was determined with the help of the gradient which we calculated over here, and then we substituted the value of W1 and W0, and eventually we got the value of W2 as this. Now I calculated till just 2 iterations. It could be extended to be calculated for more than 2 iterations, and the result could be generalized. So in this video, we talked about 3 optimization algorithms other than the gradient descent algorithm we know. This was the first algorithm which had an updation rule which was looking like this. This is the resilient propagation algorithm. Then we proceeded further with the updation rule corresponding to gradient descent with momentum, and the updation rule was like this. And eventually we just learned the Nesterov accelerating gradient, which had an updation rule which was looking like this. So even though we were considering only a univariate case over here, this result could be scaled up to multivariate cases as well in exactly the same way we did in the previous video. The derivations and calculations I'm not explicitly going to cover over here. We'll cover the derivations and mathematics in a separate video, because as of now we just wanted to understand and plug and play different optimization techniques possible and try to understand how quickly they give the convergence and how exactly they work. Most of the algorithms were derived from gradient descent. As you can see over here, both the Nesterov one and the momentum one was derived very much from the gradient descent. In the next video, we will be discussing about two more algorithms which are very commonly used in real life applications. Thanks for your time.